Good morning. Welcome to the exercise class. So today my plan is for essentially to go through the topics of the problems in the exercise sheet for this week. So first, there is a problem about strong and weak measurements. Then we'll talk about how to construct a unitary, which would perform a measurement of some observable. In this case, we'll be looking at parity. And then we turn more into this thermodynamical setting that you already seen in the lecture, and look at the setup with a battery and a system, and look at how the energy exchange can be described for these two systems. Okay, so let us start with strong and weak measurements. So what is the intuition of the difference between strong and weak measurement? Sorry, let me turn off the notifications because I think so what is the difference between strong and weak measurements? So a strong measurement is a projective measurement. So essentially you have, for example, you have a qubit and which is initialized in a superposition between the state 0 and 1, and then you perform a measurement which would either directly collapse the state into the 0 state, or or collapse the state into the 1 state. And if we model such a measurement as a unitary, how to model a strong projective measurement. As in, for example, you still want to model this measurement as a unitary. For this, you just need to add one more qubit where you would kind of write down the result of your measurement. So in a sense, what this means is that you want to kind of find a unitary process which would on the system A only perform kind of this projective operation, where pi1 and pi2 are projectors which correspond to the outcomes pi0 and pi1. So in this case, for the case of the qubit, these projectors are 0, 0 on A, 1, 1 on A. So as a channel, of course, this is not a unitary operation. But we can make it unitary, as I said, by adding one additional qubit. You can call it E, for example, and then performing kind of a joint unitary on both of them. Yeah, and then tracing out the environment, like the second qubit, which you can call the environment, the pointer, or whatever. And so, and my proposal is that actually we can model the strong measurement by just a C0, acting on both of these two systems, and then kind of tracing out the second system. What is the intuition? Why is it a C0? Well, you can see the second system as sort of a memory. So you measure the first system A, and then you kind of coherently write the result into your memory. So if you get outcome 0, you write down the result 0. If you get outcome 1, then you write down the result 1. Or like in more operational interpretation, you just flip the state of the pointer from 0 to 1. And this is actually exactly how kind of C naught is constructed. So essentially, if we write down C naught, then C naught as an operation, it's just 0, 0, and A. So if A is in state 0, then nothing happens on the second system. If A is in state 1, then we apply the flip operation, X, which flips the initial state of the pointer 0 to the state 1. Yeah, and let us calculate what is the joint density matrix of the systems A and E after applying the C naught. So C naught, then we have rho A tensor product 0, 0, E, and C naught Hermitian conjugate. So C naught Hermitian conjugate is the same as the C naught. So what we end up with is 0, 0 by 1 plus 1, 1 by X, rho A 0, 0 here 0, 0 by 1 plus 1, 1 by X. Okay, so here let's now open the brackets. And also before we open the brackets, let us note that because the bracket product of 0 and 1 would be 0 because 0 and 1 are orthogonal states on the system A, then essentially this means that the only two terms which survive are this by this term here, and the second term that survives is this by this one here. And so we can write them out as a final result. Oh, sorry. Actually, I was jumping too fast. This is actually true only for when you take out the trace. So since we're not yet taking out the trace, we have to be not lazy and write out all the elements in the sum. Sorry, so actually like all the elements in the sum survive for this kind of intermediate step. So what we get here is 0, 0, rho A, 0, 0, A by 0, 0 on E plus 1, 1 A rho A 0, 0 A by 1, 0 on E because we applied the X operation. Then 0, 0 on A, rho A 0, 0 on A by 0, 1 on E plus 1, 1 A, rho A 1, 1 A by 1, 1 on E. Okay, so this is the density matrix of the systems A and E jointly after applying this C naught operation. Now, since we only want to look at the, finally we only want to look at the system A, then we need to find the reduced density matrix of the system A. So we need to trace out system E from rho A prime, which is essentially this equation here. Okay, so there is a question, why aren't the bra and ket being transposed in the second term? You mean like when we write, so here when we write C-naught, C-naught Hermitian conjugate, C-naught Hermitian conjugate is the same as C-naught, because like if we take a C-naught and we transpose it, then essentially what we get is 0, 0 transposed by identity transposed plus 1, 1 transposed conjugate also, and X transpose conjugate. But 0, 0 like transpose conjugate is also 0, 0, 1. This Hermitian conjugate is also 1, and 1, 1 Hermitian conjugate is also 1, 1, because they just exchange. And X Hermitian conjugate is also X. Was it the question? Oh, yes. Okay, great. Then let's continue. So we need to trace out the system E, which means that we need to apply the following operation. 0, so 1 on A, 0 on E, rho A E prime, 1 on A, ket on E, plus the same, but for the basis state 1 on E. Okay, so essentially here, the only terms that will survive out of this rho AE prime are those which have kind of either only 1, 1 state on E. So this one. And the ones which have a 0, 0 state on E, which is this one. Because for all other states, when you kind of, for both of these terms, you have to squeeze a state in between like the 0 on E and 0 on E, or 1 on E and 1 on E. And if it's, for example, 0, 1 is here, or like 1, 0, then because it concatenates with 0 on one side and 1 on the other, and 0 on the other side, it gives you 0, or 1 on one side and 1 on the other side, it also gives you 0. So the point is that only these terms which have the 0, 0 and 1, 1 survive. And so we arrive to the following: 0, 0 rho A, 0, 0 A plus 1, 1 A rho A 1, 1A. And this is exactly what we were looking for, because the projective measurements are described by the projectors 0, 0 and 1, 1. And then rho A prime is exactly pi 0, rho A pi 0 plus pi 1, rho A pi 1. Okay, this looks great for a strong measurement. So one can see also strong measurement, as I said, just writing down the result of your measurement into the memory, which is represented by another qubit. But crucially, you write your result into the orthogonal states of the memory. So writing down the measurement result to So the idea is that then you can also imagine another like more general type of a measurement where you also use some other qubit as a memory. But essentially then you write down your results not into the orthogonal states of the memory, but into the states of the memory which have some overlap. So for example, imagine the situation when you're measuring a qubit in a 0-1 basis, and then you write the result in another qubit, but in a way that if you get 0, then you write down like you initialize the second qubit in a state 0, and if you get the result 1 of the measure as a measurement outcome 1, then you write down kind of that result as a plus state of the second qubit. And this essentially means that kind of you copy coherently into the second qubit, but you copy into the states of the second qubit which are overlapping. So these are the states 0 and plus is a state, if you remember, it's 0 plus 1 over square root of 2. And in that case, in the case where a measurement happens like that, it is not guaranteed, of course, that the reduced matrix of A would be exactly represented by this projective by just this projective measurement into 0 and 1. And these kind of measurements, when you kind of write down the results in this non-orthogonal way into the memory, are called weak measurements. And we will look at one way how we can model them. So the question is how to model so maybe here also notes that if non-orthogonal, so weak measurement. And for this, we can consider a following operation. So imagine again that I have my qubit A, which I'm trying to measure, in 0-1 basis, but I kind of do it in a way that if I have a memory here, which I again label as E, then I write them down, the results I write down kind of in this non-orthogonal way. And we describe this operation as, here we consider the operation which is a controlled rotation gate. So the controlled rotation gate is a following operation. So it's the same as the as a C0 gate, because C0 gate is essentially, as you remember, just a controlled X operation. And this instead of the X operation, we just apply the rotation about X axis in this block sphere representation. So we can write down this unitary operation acting on these two qubits as, like, if the first qubit is in the state 0, we don't do anything to the second qubit. And if the first qubit is in the state 1, then we apply this rotation about x-axis to the second qubit. And this is exactly kind of situation I was describing before. So imagine that your initial qubit is in the state 0. So that's the system A is in the state 0. Then after applying this operation, nothing happens to the second system because it's initialized in the state 0. So kind of 0, 0 on the state A maps as a memory entry in the system E to the 0. However, if the initial initial system was in a state 1 in the beginning, and we apply this operation U, then the operation that is applied on the second qubit is exactly this kind of rotation operation. And as we remember, so this rotation operation is just written as e to the power minus I theta over 2x, which in matrix form just corresponds to this matrix. And this matrix, Rx0, if the initial state of the system E is 0, then it maps it to cosine theta over 2, 0 minus I sine theta over 2, 1. Which means that if the initial state of A is 1, then then we have to apply, because it's a controlled operation, we have to apply this rotation to the second qubit, and then this essentially the state of the second qubit becomes this. So one can see that kind of if we start initially from this state, this is mapped to 0A, 0E because nothing happens. And however, if the initial state of the system A is 1, then this is mapped to 1, and this like cosine 0 minus I sine 1. So it's kind of, we still write into the memory coherently, but the states that we write into, namely this 0E and cosine theta over 2, 0E minus I sine theta over 2, 1, they are not orthogonal. So in a case where it was a C0, they were orthogonal. In this case, we're kind of writing down to non-orthogonal states. Okay, so now let us do the same procedure as we did before. So let us calculate rho AE prime, which is the state of these two systems after applying the operation U. And again, it will be U RA tensor product 0, 0 on E, U dagger. Okay, let's write it out. Be 0, 0 tensor product identity plus 1, 1 tensor product Rx theta. Then we have rho A 0, 0. And the last one is U dagger, which is 0, 0 tensor product 1, because the Hermitian conjugate of 0, 0 is 0, 0, and Hermitian conjugate of the identity is identity, plus 1, 1, but tensor product Rx of theta dagger. So here we like have to write out dagger explicitly because Rx of theta is not a Hermitian operator. So like it's not equal to its own Hermitian conjugate. Okay, then let us write this out. I wonder if I should start a new page. Okay, maybe I'll start here and I'll continue often. So here what we get is 0, 0, rho A, 0, 0, tensor product, this by just 0, 0. So this is all on A, this is E, plus 0, 0, rho A, 1, 1. Tensor product 0. Oh, sorry. Let me do it this way. P0, 0, Rx dagger of theta. Plus 1, 1, row A, 0, 0, tensor product Rx of theta 0, 0, plus the last term in the sum is 1, 1, row A, 1, 1, tensor product Rx of theta 0, 0, Rx dagger theta. Okay, good. Now let us instead of Rx of theta acting on 0 and Rx dagger of theta acting on 0 also like inputs the exact expressions for that. So we've seen that Rx of theta acting on 0, what we get is cosine theta over 2, 0 minus I sine theta over 2, 1. And its Hermitian conjugate, so Rx dagger of theta acting on the bra of 0, we get cosine theta over 2, 0, plus I, sorry, I need to write here the bra, plus I sine theta over 2, 0. Okay, so there was something in the chat. So the question here is in the chat, but if we chose theta equals k by pi, then this would correspond to a strong measurement. Yes, exactly. This is true. It's actually one of the questions in the exercise sheet. But exactly, if we choose theta equal like the multiple of a pi, then this procedure would correspond to a strong measurement. Okay, anyway, but let's continue with our painful task. So now I'm coming back to what I wrote before and just substituting this Rx acting on 0. So what I get is here we don't have anything, then the next term, row A, 1, 1. Here we have tensor product cosine theta over 2, 0, 0, plus I sine theta over 2. Let me check. So this was Rx acting there. And then this will be 0, 1. Plus the next term. And here we will get cosine theta over 2, 0, 0, minus I sine theta over 2, 1, 0. Plus the final component, which is a bit painful, but hang on. Here we act with Rx on both sides. So. Oh yes, because I love to mix zeros and ones. And 0 is so much nicer to draw. Sorry. Okay, so we came to this. Yeah, I don't know if we should massage this before we take the partial trace. Yeah, I think we can survive, perhaps. Yeah, so now what we do, we take this monster and we take its partial trace, tracing out the second system. So the pointing. Okay, so what we get here is, again, let us consider which terms actually survive from this monstrous expression. So again, like when we're computing the partial trace, we're only looking at terms essentially for which are tensor product with 0, 0 on E or 1, 1 on E. So the terms are which survive is this one because it's tensor product with 0, 0 on the second system. Then the next one is like this. The next one is this with this. And the last one is, there are actually two. So this one with this by this, with two cosines, and with sine squared, because it's also, so it's a part which is tensor product with 1, 1 on the second system. So we just write out the surviving terms. So of course you can also, like when you do it by yourself, then you can also, it's totally normal if you just write the expression for the, like the explicit expression for like tracing out, and then see how this acts on every term in the expression. But here I'm just trying to show how to do these things more efficiently, like how you can see what is essentially the partial trace. Also, maybe I didn't mention it before, but like if you, like if you're considering systems which are with a higher dimension than qubits, I don't know, if you're considering system which consists of 10 qubits or even 3 qubits, can be sometimes already quite cumbersome. Then actually you can use Mathematica, and you can use this add-on plugin Mathematica, which is called Quantum Information plugin. I think it was developed in University of York. You can find it somewhere in the open access. And there they explicitly have this already written just functions for taking out a partial trace, for example. Yeah, so if you have matrices, big matrices, and you want to take a partial trace, then yeah, you should use that software for Mathematica. Yeah, and also maybe if you don't know, actually you can, since you're an ETH student, you can use like the official license Mathematica for free. You just need to, I think the instructions are in so-called IT shop of ETH. And the same goes for MATLAB and most of other like plotting programs. So yeah, so you don't have like to go to the Wolfram Alpha website, which is shit, and try to input some integrals there. Just download the Mathematic or MATLAB and use the license version, which is provided by ETH. Okay, this was a long detour. Let us go back to writing down our reduced density matrix. So here we have cosine theta over 2, 0, 0, rho A, 1, 1 plus cosine theta over 2, 1, 1, rho A, 1, 1 plus 1, 1 rho A, 1, 1. Actually, let me write it down explicitly. So here we would have kind of 1, 1 rho A, 1, 1. And then we would have cosine squared of theta over 2 plus sine squared of theta over 2. Because here we would have minus I sine theta over 2 by plus I sine theta over 2, which would give us plus sine squared theta over 2. And this is 1. So essentially it just goes away. Yeah, so this is our final state. So what we have is we had a rho A and it got mapped to 0, 0, rho A, 0, 0 plus 1, 1 plus cosine theta over 2, 1, 1 rho A, 1, 1 plus cosine theta over 2, 1, 1 0, 0 rho A, 1, 1 plus 1, 1 rho A, 1, 1. Okay, great. So what is it? What does this operation correspond to if we're looking at how the density matrix changes? So suppose that kind of rho A in the matrix form, we can write it out as like, I don't know, some A, B, B conjugate, C. So the connection between like these off-diagonal elements I just got from the fact that the density matrix has to be Hermitian. And one can see that actually these terms, so for example, 0, 0, rho A, 0, 0, are exactly the terms that appear in the density matrix of rho A. So for example, this is A, this is B, this is B conjugate, sorry, not exactly, but I'm just trying to convey my thoughts. So these are the terms. Actually, these are the terms which appear in the matrix. Right, so you have, this is B, this is B conjugate, and this is C. And then essentially, if we label these, if we make this connection between the elements of the original matrix and kind of this bracket and this rho A squeezed in between Brown and Ket explicit, then we can write out to what this matrix is mapped explicitly. So suppose that we start with the state which is described by this matrix. Then what we get here is A, 0, 0, because we just substitute instead of this part here, our element of the matrix A, plus cosine theta over 2. And again, I drew some 1s instead of 0s. This is surprising. So now this term, we just need to take this part this is the element of the matrix, which is B conjugate. It's here. And here we have cosine theta over 2 by B conjugate 1, 0 plus similar thing for the other. This is just B cosine theta over 2, 0, 1 plus C by 1, 1. And as in a matrix form, this is just A, B cosine theta over 2, B star cosine theta over 2C. So essentially what this operation does, it only affects the off-diagonal elements in the density matrix of the state A. And now we can see this connection with the strong measurement. Because what the strong measurement would do to this matrix, it would just leave, it would only leave the diagonal elements. So A, 0, 0, C. Because it would just like have this part which projects the state into 0, 0, and the other part which projects the state into 1, 1. Like 0, 0 or 1, 1. And there would be no off-diagonal elements. Which means that like if we want this measurement to be strong, like then theta has to be like a multiple of pi. So for example, it has to be pi, or 2 pi. No, 2 pi does not work. So 3 pi. God, I hate this. So cosine theta over 2 has to be 0. So for the off-diagonal elements, have to be 0 in the end. And so theta over 2 has to be pi over 2 plus pi n. So theta has to be pi plus 2 pi n. Yeah. And for this angle theta, if we choose that angle theta, the measurement will be strong. Otherwise, kind of the measurement will be characterized as weak. So the idea of the weak measurement is also that, so for example, for the strong measurement, if we have this writing down, if we interpret the second qubit as in writing down into memory, then in the end, what we can do is we don't have to measure the initial qubit, but we only can measure the memory in which we kind of copy the state. And for the strong measurement, if we measure the second qubit, which acts like a memory, then we kind of get this correlation with probability 1. So if we measure the memory in the state 0, then it also effectively collapses the first qubit into the state 0. If we measure it in a state 1, then it also effectively collapses the first qubit into the state 1. However, like when you write into like non-orthogonal states of the memory, then if one measures, for example, 1 on the memory qubit, then it doesn't correspond to, or like, okay, so if one measures, for example, plus, or if one measures this Rx of theta acting on 0 on the second qubit, then it doesn't effectively collapse the first qubit into the state 1. So just to give you maybe a bit of connection to like this memory qubit. Okay. So now let us turn to the next topic, which is kind of connected to this one, and which is the second exercise, which is about measuring parity. But this does not only concern parity, but also concerns like generally observables that we measure. But anyway, so let us consider this observable P, which we can write as pi 0 minus pi 1, which is a parity observable on two systems, on two qubit systems A and B. So yeah, I think you've seen this observable in the class. So the idea of this observable for two systems is the following. So it kind of this observable corresponds to the eigenvalue 1 if these two qubits are in such a state that if you exchange these two qubits, kind of do this permutation, then the state does not change. And kind of the state is even. And then, but if you exchange these two qubits, if the state becomes the opposite, then essentially the parity is odd. So so this is defined for kind of two systems. Okay, so now the question is the following, and then pi 0 and pi 1 are kind of these projectors, projector corresponding to even and projector corresponding to odd. Kind of even state corresponding to odd state. And the idea here is to kind of introduce a third qubit, which we call S. So we have these two qubits A, B. Then we have a third qubit S. And come up with such a unitary which would, if the system S, the third system S, is initialized in state 0, it would this unitary would correspond to measuring the parity of these two qubits A and B, and then and then writing the result into this qubit C, which can serve as a memory. And if the parity is even, then you don't do anything to the state of the system S. If the parity is odd, then you have to flip the state of the S from 0 to 1. So essentially apply the X operation. And one has to write down the how does this unitary looks like. So my proposition for this unitary is the following, and again you'll see that it's it's constructed in a very similar way as as a C-node operation. So since we have the projectors which correspond to the even and odd states, then we do the following. So if the first two systems, so this is acting on the first two systems, right, on A and B. If the first two systems are kind of in an even state, then essentially nothing happens on the system S. If the systems A and B are in an odd state, So they're like projected into the odd state. Then we apply an X operation on the system S. So we flip it. Why is this the same as C naught? Well, C naught, again, how do we write C naught? We say if the first system is in state 0, then we don't do anything on the second system. And if the first system is in state 1, then we flip the state of the second system. However, this is the same as saying, oh, we measure the first system in a Z basis and write down the result to the second system. And 0, 0, and 1, 1 are exactly the projectors which correspond to outcomes 1 and 0 for measurement in Z basis. So this gives us the recipe of kind of how to construct the measurement if we're looking at some observable, kind of how to construct this unitary measurement. So you just have to find the projectors which correspond to this observable, and then write down this controlled operation on the memory qubit, and which would describe what happens to this memory qubit in case kind of for different projectors which correspond to different measurement outcomes. So yeah, so you can check this unitary operation U on some arbitrary state psi AB that the systems A and B start with. But generally, this is just a general way of how to write this kind of unitary measurement operation, or like this coherent memory update operation. Okay, so this was a fast exercise. And now we're coming to kind of the last exercise, which is of more of this thermodynamical nature, but also just the physical nature. So let us look at the following setting. So suppose that we have two systems. So one system we call a system, and the other one we call a battery. And so the first system is S, and S is just a qubit, which means that it is a two-level system where these two levels are separated by a certain energy gap. So the idea here is that qubit has this 2 degrees of freedom, and these 2 degrees of freedom are, in this case, energetically different. So you can draw it as, so usually in physics we draw it as just these two levels, and we have a convention that the kind of the energy axis is always looking up. So essentially we have two levels. The first level we'll label as 0, second level we'll label as 1, and the energy difference between these two levels, let's say, is delta. This was the first system, just a qubit. Then the second system is so-called battery. So battery is this infinite dimensional, or here we approximate it as an infinite dimensional Hilbert space with discrete levels. And here we assume that these levels are like much closer to each other. So they're all equidistant, all these levels, and they're much closer to each other than the energy gap delta for the qubit. And then, for example, and we call the energy levels of this battery as EK. Ek plus 1 and so on. And k goes from minus infinity to plus infinity. Of course, this is an idealization. And yeah, in the context of thermodynamics, it would correspond to like this different thermal levels of a molecule, for example. But yeah, we call it a battery. And actually, let me change the notation a bit. So let me be consistent with the lectures, and let me call this epsilon. And this gap I'll call delta. And all these levels are equidistant from each other for the battery. And of course, we're working in the assumption that this battery is kind of the gaps in the battery are much less. The energy gaps in the battery are much less than the energy gap for the qubit. And the idea of the exercise is to describe a particular type of transformation that can happen between these two systems. So the transformation is as such that as it describes kind of an interchange of energy between these two systems. So suppose that like we're in a lab and we only have these two systems and they're isolated from everything else. So there is so the total energy is conserved. But we draw this again. So we have a qubit 0, 1, and we have a particle here. Like so, which means that like the state of our qubit is 0. And then we have a battery. Then we have a battery where the initial state of the battery is Ek, suppose. So which means that kind of the particle is at this energy level in the battery. So these are two different particles. Maybe I should this is red, let's say. And then what we want to do, we want to put our qubit into the excited state. So we want to kind of take this particle, which is at 0 level, to the upper energy level. So again, the energies go as this. So we want to put it here. But for this, we need some energy, and we can take this energy kind of by lowering the state of the battery to some state Ek minus Q. And we need to lower it by the same energy we raise this kind of the state of the qubit. So Q would be epsilon over delta. So if this is epsilon, this delta, then this is kind of the number of levels that we have to lower the state of the battery. Okay, and one can also think of the reverse process. If we want to lower the state of the qubit from the excited state 1 to the ground state 0, then we can perform the reverse of this operation. So we can put this particle down, but then we can raise the state of the battery back up. And in this exercise, we just formalize this transformation, which describes this energy exchange. Before describing this transformation, we also need to write down what is the Hamiltonian of this total system, SB. So for this problem, we'll assume that kind of initially there is no kind of interaction happening between these two systems. So the Hamiltonian of these two systems is local, which means that it is just the sum of the Hamiltonians on the system S and on the system B. So it's going to be HS for identity on V plus identity on S HB. And the Hamiltonian on S would be epsilon 1 by 1B plus 1S. Hamiltonian on B will be the following. I'll explain in a moment. So why do we write Hamiltonians like this? So the essence of the Hamiltonian can be understood in two ways. So when we write a Hamiltonian for the system, first thing that you have to remember that Hamiltonian of the system somehow describes the energy of the system. The energy of the system and also kind of the what activity is happening in the system. And in this case, if we look at the Hamiltonian of the system S here, which is just epsilon 1 it simply captures the fact that if we take the energy of the ground state 0 here as 0, then the energy of the excited state 1 would be epsilon. And then essentially what this is actually is the 0 energy of the state 0 plus epsilon energy of the state 1. So kind of Hamiltonian tells you about this distribution of energy in the system. And this Hamiltonian also tells us that actually kind of there is no way for the system to just under this Hamiltonian without the battery, without anything else, to kind of hop from the state 0 to state 1. Because if one could do this, then Hamiltonian would have terms like 0, 1, like something by 0, 1, plus something conjugate by 1, 0. This would kind of record the evidence of like this potential activity of hopping from the ground state to the excited state and back. But we don't have this thing here, which means that kind of this Hamiltonian is like static in that way. So it just, in this sense, captures the fact that there is an energy difference in the states for the excited and the ground state. And the same for battery. So battery, we model it as this infinite amount of these levels, which are separated by the gap delta. So essentially, if there is some kind of like 0th level, then the energy kind of of the levels from 0 to plus infinity would be described as delta k. Then from minus infinity, from 0 to minus infinity would be like minus delta modulus k, and hence we can just ascribe like to each level this energy delta k, where k goes from minus infinity to plus infinity. And this is exactly the term that would go or goes into the Hamiltonian. Okay, so now since we know the Hamiltonian and we know which process we want to describe, then we can go and describe this process. And again, like the description of the process can be written quite easily. So the first part of the process is what happens if we want to, for the qubit to go from 0 to 1, and at the same time lower the state of the battery. So this would correspond to 0, 1 acting on S which exactly, like if we just take this part and assume that we are acting on the zero state of the system S, then it would take our zero state into the state 1. Okay, and then what we need to do, we need to like ensure that in this case, in whichever level EK the battery is, it has to go like this Q levels down, where Q is this epsilon over delta, this number of levels which corresponds to the energy gap in a qubit. So essentially, if it was in the state EK, then it has to go to the state EK minus Q. And we sum over Q, so we sum over K because we need to ensure that this happens in whichever state EK the system is, the battery is. Okay, and then we also need to add the reverse process. So what if the system, the qubit, is initially in the state 1 and it wants to go down to the state 0? Then for the battery, we need to ensure that for all states EK, the energy state of the battery goes Q levels higher. And hence, yes, so this is essentially, that's it. That's the way we write the unitary. So there is kind of this logical way of putting the description of the process into how we express it with brackets. And the first thing that we might need to confirm is, this unitary indeed a unitary? So for this, we need to check whether USB dagger equals identity. So let's do this. So I'm just writing USB now. And now the dagger. The dagger would be 10 S. Let me sum over J here, so we wouldn't be confused. So it's going to be EJ J plus Q plus 0, 1 S sum over J EJ minus Q. Okay, so now let us open massage this equation. So the first term has this and this on S, so it survives, and on S it just gives us 0, 0 S. By here we have the sum over K, sum over J, EK plus Q, EK, EJ, EJ plus Q, plus. And then we have this 0, 1 by this, so 0, 1 by 0, 1, because 1 meets 0, it's 0, so this does not survive. Then we have 1, 0, 1, 0, which doesn't survive for the same reason. And then finally we have 1, 0, 0, 1, which is great and gives us just 1, 1. And again, here we have the part acting on the battery. Sum over K, sum over J, EK minus Q, EK, EJ, EJ minus Q, T on B. Okay, so what can we conclude from here? So the basis of the battery is an orthogonal basis. We choose it like this. So this gives us delta JK, the same as this gives us delta JK. So what we arrive to is 0, 0, and S by sum over K, E, K plus Q, EK plus Q, plus 1, 1 on S, sum over K, EK minus Q, EK minus Q. We don't care about Q because K is summing from minus infinity to plus infinity. And because EKs form a complete basis, then this is actually identity, and this is also identity. So I'm acting on B. And 0, 0 on S plus 1, 1 on S is also an identity. So then we have identity on S, identity on B, identity on SB, which means that U is a unitary. Of course, one also, like, if we want to be rigorous, one also needs to show that USB dagger USB is also identity, but this is essentially the same process. You're gonna go through the same process. Okay, so USB is indeed a unitary. Great, so we wrote it down correctly. Then let us see if it indeed acts in a way that we kind of wanted it to act. So let us apply USB to the following initial state. So the qubit is in a superposition of 0 and 1. And the battery is in some state EK. Okay, so now let us write what we had as this unitary. We had 0, 0, 1 on S, sum over K, K plus Q, EK, plus 1, 0 on S, sum over K, EK, minus Q, EK. And this we need to apply to alpha 0S EK on B plus beta 1 on S EK on B. Okay, let us do this. So there are some terms in this expression which are killed, right? So for example, if you act with the first term, like with this term here on this, you get 0. The same as if you act with this term to the term 1s, you also get 0. So we only act, we are only allowed to act with this term on this term. So this is the first one that we write down, would be beta 0 on S. Tensor product. What we have here is, this is not the best choice of the coefficients here, so I'll just say that this is J, because I don't want to get mixed up with the K over which I'm summing and the K that is level there. J plus K Q J EJ minus Q EJ. And here I get sum over J EJ plus Q EJ EK plus the second term is alpha 1 on S by sum over J EJ minus Q EJ EK. Again, this gives us delta JK. This gives us delta JK as well. And what we get is here we just have EK plus Q on B plus alpha 1 EK minus Q S and B. And what this tells us, this tells us that actually a unitary acts exactly as we predicted. So in a sense, if the initial state is in a state, if the initially the system is in state 1, then it turns it to 0, and then and subsequently it the state of the battery, the energy of the battery goes up. And if it's in a state initially in the state 0, then it goes up to the state 1, and the energy of the battery is lowered. Okay, great. Now what we want to also just convince ourselves are like what is the change in the energies in the battery and of the battery and also of the system. So here comes the question: how do we calculate the kind of the energy, the average energy value? So the expectation value of energy. And here one needs to remember again that the observable that corresponds to the energy is the Hamiltonian. So then the expectation value of energy is just trace of rho h. Or if you write it like in this more vector form, then this is psi h psi. If the, like this is if rho is psi psi. Okay, so now let us calculate the energy, the value of the energy in the beginning. So if we look at the expectation value of energy of S, of the system S in the beginning, it was initially in the state alpha 0 plus beta 1. So this would be alpha 0 plus beta 1. Then the Hamiltonian of the system is local. So we can just write the part, which corresponds to the system S, which is epsilon 1 1. And then we just write again alpha 0 plus beta 1. Okay, and the only term that survives here is this by this by this. So what we get is beta squared or modulus squared epsilon, which makes sense because here the system is in the state 1 with a probability beta. So with the probability beta modulus squared. And then essentially the system just has energy 0 with probability modulus alpha squared and energy epsilon with probability beta modulus squared. which means that the mean value of energy would be modulus beta squared epsilon. And for the battery, it's even easier. So you just take psi. So the state of the battery, which is EK, the initial state of the battery. Then you take the sum over J, you take the Hamiltonian of the battery. Again, because it's local, we can just look at it separately. EK, sorry, J, and then we have the state again. And this just gives us, this part gives us delta Kj. So the whole ordeal arrives to K delta, which also makes sense because like the state of the battery is initially just initialized in this state EK, which corresponds to the energy of this level. Okay, and as an exercise, you can also calculate the energies of the battery and of the system after this they undergo this joint evolution, which is described by USB. And for this, you just need to take like the final state that we've written here. Then you need to take the partial trace and find the reduced states of systems S and B. And then for each of these reduced matrices, you can just find its the expectation value of energy using this formula with a density matrix. And the last remark for today is the following. So imagine that we are in an arbitrary setting and we have an H given, which is the Hamiltonian of the system, and U, which is transformation that we apply to the system. And then we want to ask ourselves is, okay, so we know that kind of if the system is isolated, then the energy must be conserved. So which means like this expectation value of energy has to be conserved at all times. And the question is, if we apply this arbitrary transformation U, in which cases will it correspond to a transformation which preserves the energy in the system? And the corollary is the following, that if U and H commute, so the transformation that we apply commutes with the Hamiltonian of the system, then the global energy is conserved. And this is very easy to prove. It's just like two lines, so I'll do it here. So suppose that we apply the unitary U, and initially the system is in a state rho. Then the state of the system after applying U would be U rho or U dagger. Then the initial energy of the whole system, the expectation value would be just trace of rho H, because H is the observable that corresponds to the energy of the system. The expectation value of energy after the transformation is applied can be written as, like, if this is rho prime, then this is rho prime H, which is the trace of U rho U dagger H. Then here we can write that this is equal by the property of the trace when you can cyclically kind of interchange the matrices in the trace. This is equal to trace of rho u dagger hu. So we just put u here. This is just a property of a trace. Then we use that h and u commute. So h and u commute. This means that UH is equal to HU, which means that trace, this is equal to trace rho, U dagger, UH. U is a unitary, so this is an identity. So we arrive to trace rho H, which is exactly the initial expectation value of the energy. So what we arrive to is if the unitary transformation commutes with the Hamiltonian, then we are guaranteed that the global energy in the system is conserved. And this is a good kind of thing to check. So when we are writing down the unitary for this exercise, we wrote it down from kind of physical considerations, and it looked as the energy was conserved because we made sure that the energy level of the battery would lower down or get higher according to like how the energy changed in the qubit. But of course, for some more complicated unitaries, which are maybe just written down, whatever, as a matrix and don't have a very clear physical interpretation, for this kind of unitaries, it's always good to kind of compute whether they're commuting with the Hamiltonian of the system and whether this the total system is indeed isolated or not, or there is some energy exchange with the outside. And still for this unitary that we formulated, one can also check whether it commutes with the Hamiltonian. Of course, it commutes with the Hamiltonian because its physical interpretation is quite clear. Okay, I think I kept already long enough. I think this is all for today. If there are any questions, always welcome to write an email. Can discuss them anytime. Also, Lídia told me to remind you that the lecture notes, like the typed in version of the lecture notes, kind of at least I think the few first chapters is already up on Moodle. So it's not only handwritten version.